In this series of lectures, we're going to talk about inequalities and how we can use them to help ourselves solve integer programs efficiently. Before we do that, though, we're going to remind ourselves about a few facts related to inequalities and formulations. Suppose that we'd like to solve an optimization problem. Specifically, we'd like to maximize the function f of x subject to a set of constraints on an integer lattice. The set of feasible points are pictured in this graph. The set of feasible points are x. A formulation to this problem is any polytope, in this case p, so that this polytope intersected with the integer lattice results in just the feasible points, x. In this case, p is a formulation. We can recall how these are related to the constraints written in our integer program. P is the set of linear constraints, and x is the set of linear constraints combined with the integer constraints. We saw one way to solve an integer program is potentially to take the linear program relaxation and solve it and hope that the solutions are integer points. In this case, the linear program solution is exactly equal to the integer programming solution. We saw that this is going to be the case when our formulation P is exactly equal to the convex hull of the points in X. In our graph, we see the convex hull as this green shape. The corner points of this polyhedron are exactly the integer points in X. If this is the case, then it's easy to see that the optimal solution to our integer program is the optimal solution to our linear program. That's because the optimal solution to the linear program is one of the corner points, and those corner points are automatically in X. If this is the case, if P is equal to the convex hull of X, then in some ways, the integer program is an easy problem to solve. Unfortunately, the story isn't that simple. Even if we have the convex hull of X, it's not really a practical object in most circumstances. The reason why is that to write the convex hull of X, we can potentially need an exponential number of constraints. If we have an exponential number of constraints, then the resulting linear program, although it will result in integer solutions, is actually a hard problem to solve. Instead, our goal isn't really going to be to find the convex hull of X, put it into a linear program, and then solve it. Instead, we'd like to find just something called a better constraint. So better constraints are our goal, not necessarily the convex hull of X. We can see how better constraints are going to help us. And in this case, better means something very particular. A set of constraints are better if the polyhedron is contained inside of the original one. So, for example, when considering the polyhedron P and the polyhedron P prime, the set of constraints defining P prime is better because P prime is completely contained within inside of P. We've seen in earlier lectures how better constraints help us. If we're maximizing some function f of x, and we're looking at the polyhedron P, the optimal solution ends up at this point, which we call z2 of LP. The optimal solution when we're looking at P prime is this point, z1 of LP. z1 of LP is closer to our real optimal solution, z star, than z2 of LP. We can write this in terms of absolute value. The distance between z star and z1 of LP is smaller than the distance of z star and z2 of LP. In this way, z1 of LP is a better solution. This allows us to write a better bound. By having better constraints, we can write a better bound on our original problem. Once we have these better bounds in hand, we can use them to find better approximation algorithms or put them inside of a branch and bound framework. If we have better bounds, then we'll be able to prune more nodes. Or alternatively, if we have better bounds, we'll be able to round our linear program and get a better solution. In what follows, we're going to be interested in looking at adding constraints to our formulation so that we make a better formulation. The motivation for this is that better constraints result in a better formulation. A better formulation results in better bounds. And if we have better bounds, we can put it into a branch and bound framework and prune more nodes, as an example. And because we can prune more nodes, we can potentially get faster algorithms. Unfortunately, by putting more constraints into our formulation, there's a trade-off. More constraints mean that we can solve our LP, but our linear program is potentially going to take a longer time to solve. If our linear program takes a longer time to solve, although we get better bounds, they take a longer time to calculate. We're going to keep this trade-off in mind. Better constraints, or adding better constraints, is going to result in faster algorithms because we get better bounds. However, there's a trade-off in that when we add constraints, we're going to have to take longer to solve our linear program, and so these better bounds are going to take longer to compute.